Okay, we're going to look at a class of problems which have where you have a ball going up and being tossed in the air, a cart going up an incline. So ball in air slash cart on incline. In class, we've seen that sometimes it's useful to draw a velocity versus time graph. And so the velocity versus time graph for a ball tossed in the air or a cart on an incline looks something like this. Starts off with the initial velocity, and then the object is slowed down by gravity, whether or not it be gravity of minus 10 meters per second squared due to a free fall, or if it's on an incline, it could be some number less. Let's imagine we have a cart going up an incline, and let's imagine that for the initially we have a velocity v0 of 3 meters per second, an acceleration of minus 1 meter per second squared. Obviously that means that this slope here is minus 1 meter per second squared, and the initial velocity v0 is 3 meters per second. So one of the things that should be kind of obvious from the get-go is that if I have an initial, I guess what is that? This intercept here is 3, and it's got a slope of 1, that after 3 seconds it's going to be at its maximum height. And so I could do a whole bunch of different things. So we could talk about what height, what displacement, if we're doing a cart on an incline, what displacement does the cart have when it gets to the very top? How far does it travel? So there's two ways of looking at this. One is just to use our v squared is equal to v squared 2a delta d. At the top, v at the top is going to be 0. v0 is 3 meters per second. The correct units are meter for velocity or meters per second squared. Meter per second squared, and I can just plug everything into the equation and into this equation and see what I get. So let's just give that a try. 0 is equal to 3 squared plus 2 minus 1 delta d. Delta d is equal to, so the maximum displacement is 4.5 meters. Displacement is meters, not meters per second. Do this. We know that v top is 0, v0 is 3 meters per second squared, and we know that the time to get to the top is going to be, t is going to be equal to v final minus v0 divided by a. 0 minus 3 over minus 1 is 3 seconds. And we also know that the displacement, delta d, is equal to average velocity times t. Remember, this only works for constant acceleration, but we have constant acceleration here. The average velocity, v average is v1, v2 over 2 times t. So that's going to give me 0 plus 3 over 2 times 3, which is 4.5 meters. And I notice that that's meters per second, so I'm going to fix that to meters. So that's fairly straightforward. Now, there's a whole bunch of other problems that we can do, and I'm going to move to a new sheet, redraw a couple of these things, and then we'll talk about that. Same deal. Initial velocity 3, intercept of 3 seconds, 3 meters per second, 3 seconds, and this time I'm an acceleration of minus 1 meter per second squared. And then the question is, how would I figure out the velocity at t equals 1.5 seconds and the velocity at t equals 4 seconds? So this is on the way up, this is on the way down. And then where exactly am I at 1.5 seconds and at 4.5 seconds? So probably the easiest way to do the velocity is just to say that velocity is v0 plus at. So that would be 3 meters per second plus, open brackets, minus 1 meter per second squared times 1.5. 3 minus 1.5 is 1.5 meters per second. V0 plus AT. And now I'm going to look at the 4 for t equals 4 seconds. 3 meters per second plus, open brackets, minus 1 meter per second squared times 4 seconds is 3 minus 4 is minus 1 meter per second. I have a couple of options when it comes to figuring out what my displacement is. At this point, probably I think the easiest way to do, well, there's two ways of doing it. One is just to use the x is equal x0 v0t 1/2 at squared, and I'll do that for one of these. 0 plus v0 is 3 meters per second multiplied by 1.5 seconds plus 1/2 minus 1 times 1.5 seconds squared. And if I do that all out, I think I end up with 3.375 meters. So it's not quite to the top, but it's somewhere close to the top. Another way to think about to do this would be to, since we know the velocity, we could come back here and use our v squared is equal to v0 squared 2a delta d, where I'm solving for delta d. So I know that the velocity final, we calculated that already as 1.5, so I'll have 1.5 quantity squared minus 3 quantity squared. 0 is actually 3, not minus 3. It has no effect on the answer. Times minus 1 delta d. So that's going to give me 2.25 minus 9 all over 2 is equal to delta d. And if I do that out, I should get the same answer, 3.375 meters. And I could do the same thing for these, for a displacement, for the 4 seconds, 4 seconds if I wanted to. But it's kind of whatever you want to do. I wanted to talk about kind of one other thing, which is this idea of using the graph to figure out some of this. So I'm going to move on to a new sheet, and then we'll just kind of look at it. Same graph. I have 3 meters per second. I have this time here of 3 seconds. And I'm curious about what goes on at this point of 1.5 seconds. So certainly what I could do is I could calculate this area. So I can look at this area from a variety of different perspectives, but one is to get this velocity right here. I can say that the velocity here is v0 minus at, or v0 plus at, and in our case that would look like 3 plus minus 1 times 1.5. We know what the answer is because we've done this already, but it's going to give you 1.5 meters per second. So at this point, if I want to get the area here, all I have to say is the bottom is a height of 1.5, a width of 1.5, plus a triangle, and the triangle is 1/2 the base of 1.5 multiplied by the height, which is 1.5. 1.5 being 3 minus 1.5. 3.375 meters. The last thing I want to talk about is looking at what happens when I drop something off of a cliff. When I do a drop something off of a cliff problem, I actually want to talk about having a negative velocity because the thing is going down. So I'll start off with v0 equals 0, and then I'll have a slope here of minus 10 meters per second squared. So at this point I'm free to just kind of say if I want to get distances, I can use my equations, or I can do stuff by area. And I think problem number 6 of the homework, I think are often more easily solved using kind of area, but you can kind of do whatever you want. The last hint I want to give you about the homework that we're doing is regarding number 5. And number 5 talks about a balloon that's going up in the air. So you have a balloon that is going up in the air with some initial velocity, in this case 12 meters per second. So let's think about that. When I release this rock or package, the package has a velocity of 12 meters per second. And what's going to end up happening is that that velocity is going to remain positive as it falls, but it's going to decrease. So that if it starts out with a velocity of, say, I'm using a different number than the homework, say 15 meters per second, it's going to keep on going up until 1.5 seconds. So this has the important result that the displacement versus time, remember this was time, this was velocity, this is displacement. Well, the displacement versus time, or the distance versus time, is going to start off positive, and it's still going to be increasing for that whole 1.5 seconds. So let's draw in that 1.5 seconds, and then let's imagine that it starts out at a height of 30 meters. What the distance from the ground starts at 30 meters and keeps on increasing until 1.5 seconds. So it's going to look something like that. So again, we have a initial velocity of 15 meters per second. The thing is tossed up in the air, and we've said that it travels for 1.5 seconds before reaching the top of the flight. We can tell that that's the top of the flight because you notice that all of this here is positive area. It's only when it gets to the very top that we begin to get negative area, which means it's coming back down to Earth. So there's a couple of things that we can do with this information. One is that we can get the change in the added height. It started at 30 meters. How much higher does it go? One option is to say delta D is average velocity times t. Average velocity is 7.5 meters per second. 15 plus 0 divided by 2 is 7.5, times a time of 1.5 seconds gives me a displacement of 11.125 meters. That's a delta D. So if I want to get the total height off the ground, that would be the 30 meters I started out with plus the 11.25 meters that I gained for 41.25 meters. I could get the same answer, but it'd be a little bit more difficult by saying, okay, distance is d0, v0, t, 1/2 at squared. And I could say initial position is 30 plus an initial velocity of 15 times 1.5 seconds plus 1/2 minus 10 times 1.5 quantity squared. If I did that all out, I would end up with the same answer, 41.25 meters. And just to make one final point, I could also say that so I guess the other question is, when does it hit the ground? And I can, to get that answer, I could say, okay, the final position is 0, the initial position is 30, plus initial velocity 15 meters per second. And now I'm solving for t plus 1/2 minus 10 quantity t squared. And so I end up with a quadratic. 30 plus 15t minus 5t squared is equal to 0, and I think I can divide through by 5. 6 plus 3t minus t squared is 0, and then you can use solver or something like that to get the time that it takes for it to come back down to Earth. Thank you very much.